Hello everyone, my name is Annalise Meyer, coming to you today from Vancouver, Canada. I'm going to discuss the reality of planetary protection measures in the current era of private space startups. This report is the result of ongoing research from the Space Generation Congress 2019 Space Exploration Working Group and Associates. The Space Generation Congress is hosted each year by the Space Generation Advisory Council. This group is a collective of students and young professionals from across the globe that assesses current affairs in the space sector and provides policy recommendations to the UN from its permanent observer seat. This report is intended to take a closer look at how stakeholders in the growing private space sector currently interpret and implement planetary protection recommendations. As a collective of students and young professionals, we hope to provide a fresh perspective on these issues and emphasize the goals of the early career sect of space scientists, engineers, and entrepreneurs. We conducted a survey of multiple aerospace companies across the funding range and synthesized existing literature in order to understand what needs to be considered in the immediate future of private space. I will briefly present the major findings of this project and provide an overview of the resulting recommendations. Contributors to this project spanned 16 countries. And while skewed towards graduate and undergraduate students, it featured contributions from a wide demographic range. The current state of private space comprises a huge range of investment levels and goals. We interviewed several of the companies listed here, as well as some not pictured. These companies range in investment levels from seed through Series L, ensuring that our data span various perspectives. While those we interviewed were pure play space companies, we spoke with both companies with explicitly interplanetary aims, as well as those who, at present, have not expressed interplanetary intentions. However, as we've seen with Rocket Lab and iSpace, many initially small satellite companies venture into the interplanetary sector as their business develops. In preparation for this, we need to consider how planetary protection costs come into play. As an example, the current record of funding for Moon Express, one of the former competitors for the Lunar Google X Prize, is $51 million. Their explicit goal was to develop a method for extraction of economically important lunar resources. So they're a reasonable choice for a company that may aim to expand further into solar system resource prospecting. Compared to their current funding record, Viking Lander gold standard planetary protection measures are estimated to have cost about $100 million USD. While in the US, NASA may be able to provide some support for planetary protection costs, the complicated dynamics of public-private partnerships are likely to be even more muddied as private interplanetary missions develop. This funding discrepancy is one of the many reasons we chose to look into this topic. Throughout the remainder of this presentation, I will detail our findings in relation to the current state of affairs for private interplanetary missions and reasonable expectations for private space expeditions in the future. Some of these findings will no doubt be common knowledge to many of those who have worked at the interface of public and private enterprises in the space sector. For one, the companies that are most immediately interested in interplanetary expeditions are primarily funded through super angel investments. There are no currently legislated requirements to adhere to planetary protection recommendations for private companies, and heavyweight investors are under no obligation to operate with transparency or with accountability to public and scientific interests. Currently available resources comprehensively cover the background theory for planetary protection and reduction of harmful contamination. However, even useful case studies such as those featured in the August 2019 report from COSPAR and the PPOSS prepared International Planetary Protection Handbook tend to be difficult to understand and implement by her early-stage space startups. There is also no requirement or strong encouragement towards reporting organic burden and microbial community structure. Promoting reporting would provide useful information for planetary protection resources. This brings us to our first recommendation. COSPAR, with the assistance of national space agencies, should immediately begin development of a simple graphical user interface for submitting all contaminant data, including sequencing data, organic load and type, culturing results, and etc., for all spacecraft census assays and cleanroom assessments. Ease of reporting will stimulate easy access to this data for future planetary protection science. Fiscal incentives may be needed to promote reporting. To our second set of findings, we were pleased to discover that several companies interviewed cited the importance of planetary protection, and mentioned some design considerations needed to reduce resistant contaminants. These included reducing the total number of parts and avoiding non-bonded mated surfaces. These considerations often overlap with simple good manufacturing practices. However, similar to finding 1.2, it was noted by several companies that more specific instructions or training would be useful in terms of how to design for efficient sterilization and how to achieve the recommended bioburden for each mission category. Most design engineers and quality assurance technicians simply lack the background to understand how to minimize bacterial adhesion, eliminate spores, and even conduct the necessary tests to ensure that their sterilization methods are working at every step. Our second recommendation is thus directed towards private space companies interested in both near and far future interplanetary endeavors. We suggest that employees trained in microbiology and or biomedical engineering would be an asset to designing future-proof components. I will discuss our final set of findings in more detail. To begin, the need to protect intellectual property has hindered the investigation of novel methodology and designs from private companies with regards to their compatibility with planetary protection measures. This is in part because the testing required to fully characterize these methods requires expertise in facilities not currently possessed by most private space businesses. Secondly, we consulted primarily with early-stage private companies. Those that were not yet actively involved in interplanetary missions are generally not considering how planetary protection needs will affect the scalability of their designs. This includes companies with interplanetary endeavors explicitly mentioned as upcoming goals. Even training of employees in basic planetary protection measures and design considerations is not incorporated until late-stage mission planning. To emphasize this point, we will explore one particular case study, which was briefly mentioned in our summary talk. The logic we follow here can be extended to other specific aspects of vehicle design and manufacture. The use of carbon fiber composites for the construction of entire launch vehicles has allowed several companies, notably Rocket Lab and Orbex, to see commercial success in the small satellite sector. The successful use of carbon fiber composites in such a wide range of aerospace applications has allowed such ambitious private companies to plan on using their proprietary composite manufacture techniques for interplanetary activities. While on an engineering level, these techniques may scale up well. They have not been sufficiently investigated for their compatibility with microbial reduction methods. There are many questions that remain when it comes to the particulars of composite manufacture between companies for those applications that may be relevant in the transfer of harmful contamination between planets. For example, the molecule I've modeled here is a short polymer of bisphenol A diglycidyl ether, cured with 1-bis-aminomethyl cyclohexane. This is an incredibly common combination of epoxy resin and hardener, and has been featured in numerous studies investigating fracture strength and survival of microbes using cured resin as a sole carbon source. However, a huge range of resins exist, some for the purpose of replacing the endocrine-disrupting bisphenol A, some do particular utility in incorporating other additives, or various cure times, pre-preg options, temperatures, tensile strength, and fracture resistance, and so on. Curing agents change for similar reasons, as do surface features and coatings. Even if these methods are not initially developed in-house, the choice of when and for which components to use them is strictly protected in order to maintain a competitive edge. As one interviewee said, "I'd love to tell you, but that's our secret sauce." Surface composition and finish type, down to microscale roughness of polished surfaces, can have important implications on the efficacy of cleaning measures. The effect of this is that investigation of composites in publicly funded mission segments, such as the Blades of Ingenuity, for example, are insufficient. Liquids follow different wetting regimes based on surface microstructures, which changes the liquid penetration and the contact angle of the cleaning agent. As pictured here, surface finish directs liquid or foam to follow Cassie-Baxter or Wenzel wetting types. These microscopic variations can prevent full efficiency of cleaning methods, but full characterization requires use of electron or atomic force microscopy in many cases. Our current research involves investigating a variety of these possibilities via molecular dynamic simulations. Further, intentional or unintentional surface patterning may change adhesion of microorganisms. Previous investigations of internal medical devices like pacemakers have shown that microscale patterning causes different adhesion levels. As mentioned, characterizing this fully is a considerable task and requires specialized equipment. Small startups do not have the capital or the expertise required for these sorts of studies, and of course, IP protection of proprietary manufacturing and quality assurance techniques prevents public research labs from taking on these studies. Current planetary protection standards require cost-prohibitive training and facilities to execute successfully. This fact has one of two effects on early-stage companies. It either prevents the development of long-term interplanetary objectives, or it causes these companies to develop unrealistic budget and design constraints for their missions. The former encourages the current pseudo-monopoly, in which deep space and interplanetary missions are driven primarily by governmental agencies and or super angel-funded late-stage companies. The latter may lead to undue pressure placed on international bodies to loosen planetary protection regulations without adequate scientific backing. There is legitimate cause for concern that exceptions to these guidelines will be made within nations and excused on a patriotic basis. As such, I will end with our two final recommendations. We propose that financial support be provided on an international level to create centralized facilities for company-specific planetary protection research and vehicle sterilization when needed. Facilities could run comparably to existing bioscience and engineering startup incubators, with resident technicians to perform necessary analyses and prepare internal protected reports. We also recommend that legislation be passed by each Outer Space Treaty member state in order to require adherence to planetary protection guidelines for all public and private missions. I have one final thought to share with you today. Planetary protection standards need to remain at least as stringent as currently outlined by COSPAR regulations until the knowledge gaps relating to Martian meteorology, cleanroom and spacecraft microbiomes, and etc. are sufficiently addressed. Preventing contamination of extraterrestrial bodies that may hold information about life elsewhere in the universe should be prioritized over the race to meet technological and political milestones, and over economic gain. Thank you for your time, and please do reach out with any questions. Sincere thanks to the conference organizers and to our session chairs.